Okay, so first of all, thank you very much for the invitation both to this event and to the participation in the IEEE Proceedings issue. So I'm going to present next our contribution on unsourced multiple access. So machine type communications and Internet of Things systems require typically the transmission of small data units by a multitude of low power nodes with transmitters that are often sporadic and unpredictable. From a medium access perspective, this calls for the development of energy efficient, grant-free random access schemes. And this talk is going to be about this, as well as our contribution to the proceedings issue. In particular, we are going to discuss unsourced multiple access with an eye to the upcoming 6G standardization. Here is a brief introduction to the speakers. I'm Gianluigi Liva from the German Aerospace Center in Munich, and my co-presenter is Yury Polyanskiy. Originally, we thought about splitting the talk in two, but in the interest of time, we decided that one of the two would give the whole presentation, with the other one eventually intervening during the talk. Here you see a picture on how we decided who was going to give the talk, and you can guess who was the loser. Let's move on. So the unsourced multiple access framework was introduced by Yury Polyanskiy in 2017 in this ISIT paper, and the framework works like this. So we have a large number of users in the network. Out of this large number of users, a subset of KA users becomes active. Each active user has K information bits to transmit over a MAC frame with N channel uses. Every message is encoded with the same code, and the receiver receiver observes the superposition of the user transmissions together with noise. Here in this model, we have that each user transmission sees a channel coefficient H sub I. Depending on how we pick the distribution of H sub I, we can get a different UMAC models. So if H sub I is, for instance, a complex Gaussian, then what we're going to get is a quasi-static really fading UMAC. Anyhow, the decoder outputs an unordered list of messages given the channel observation Y, and the performance is measured in terms of per user probability of error, also called PUP, which is the probability that the message of a user is not contained in the list that is output by the decoder. Some important observations. The first one is crucial. The transmission by all the users takes place with the same codebook, and this is actually what allows to model the lack of coordination between users. The decoder doesn't match a user transmission to the user identity. This is what gives rise to the name unsourced UMAC, so unsourced MAC. And eventually user identities can be resolved at the higher layers of the protocol stack by looking at the payload that has been decoded for each message. There is a strong connection to compressive sensing, which we don't have the time to discuss deeply here. And another important point is that differently from classical MAC problems, the error event is defined on a per user basis. So we are looking at a per user probability of error. Another important observation, which is not in the slides, but I think it's important to clear a bit the context. Existing random access protocols like ALOA and variants of ALOA fit perfectly in this setting. With the introduction of the UMAC paradigm in 2017, a lot of development in terms of schemes that are able to approach the theoretical limits of the UMAC had happened during the past years. And in our paper, we provide a classification of the many excellent schemes for the UMAC based on, let's say, an arbitrary let's say, decision, which nevertheless we believe captures well what are the fundamental characteristics of every schema. We have a first architecture which is based on the slotted ALOA protocol with strong multi-packet reception capability. Another type of architecture relies on the transmission of a preamble, which is performed in an unsourced manner. And the choice of the preamble, which is performed randomly at the users, signals at the receiver side which kind of code has been used by the users for the data transmission phase. Then we have techniques that are inspired by the parallel with compressed sensing, and which more or less rely on divide and conquer approaches to somehow mitigate the huge dimensionality problem entailed by the compressed sensing perspective. And finally, there is architecture that relies on spread spectrum techniques to facilitate user separation. The 5G new radio standard with release 16, as Edward mentioned before, introduced a first grant-free random access option, which goes under the name of two-step random access. And the behavior of this technique is very close to the preamble-based architectures that we mentioned before. So users pick from a dictionary made by Zadov-Chu sequences preambles randomly, and they transmit those preambles on a so-called random access channel slot. And the preambles point to slots where the subsequent data transmission takes place for each user. So at the receiver side, upon detecting the preambles in the RACH slot, the base station is able to identify which slots have been used for transmission and then tries to attempt the corresponding data. Here we can see an example of the performance achievable by two-step random access protocol of 5G new radio or over a quasi-static rarely failing UMAC. These results are obtained by choosing k, the number of information bits per user, to be 100, and setting the size of the MAC frame to 15,000 complex channel uses. The y-axis is the number of active users, the x-axis is the signal-to-noise ratio. Here we see a black solid line which represents a theoretical benchmark on what can be achieved on this UMAC setting, and the red line shows what is the performance of the 5G new radio two-step random access protocol, which we can see is very far from the theoretical benchmark, and most importantly saturates very quickly already for moderate low number of active users. We studied the two-step random access protocol deeply, and we identified some main weaknesses in the 5G new radio solution, and we propose some modifications to the two-step random access protocol, which build on the use of a larger preamble dictionary, the transmission of data units across several slots rather than in a unique slot, using a block interleaving pattern, which is defined by the preamble. And at the receiver side, we employ treat interference as noise, successive interference cancellation type of decoding. This is the performance that can be achieved by this modification, which we call, by the way, sparse block IDMA. And we can see that there is a large gain in terms of energy compared to the two-step random access protocol. And more importantly, there is an impressive gain in the number of supported users. Eventually, by tuning the parameters of sparse block IDMA in a judicious manner, one is able to get the proper scaling, a proper scaling of the performance with the number of active users following in an almost parallel manner up to a large number of active users, the theoretical benchmark. Concluding this presentation, in our paper we provide a summary, a survey on the unsourced multiple access paradigm, highlighting its strengths at capturing the essential elements of massive random access protocols. We introduced then a classification of the most promising UMAC architectures, and we show also how it is possible to approach the theoretical limits by re-engineering the 5G new radio random access protocol. This concludes the presentation. I would like to thank you for the attention, and I would like also to thank collaborators that helped us to develop sparse block IDMA, in particular Krishna Narayanan, Jean-François Chamberlain, Zoran Rutkowski, Johannes Dommel, Patrick Agostini, Federico Klatzer, Andrea Munari, and Slavomir Stanza. That's it. Thank you very much.